Welcome back. So our second speaker is Mirko Mauri, and he will talk about remarks on the topology of irreducible holomorphic symplectic varieties. Please.
Thank you very much. So today, yeah, indeed, I would like to talk about some aspects of the topology of this variety. I will remind in a minute the definition. In this talk, X will be always one of such variety. And the general idea that I want to convey is the following, that if you study fibration and degeneration of this variety, you may obtain a very interesting, curious constraint about the topology of this space. So that fibration and degeneration of irreducible holomorphic symplectic varieties imposes curious constraints on the topology of X. And in particular, what I would like to discuss today is how the so-called SYZ conjecture that concern fibration on X implies that the fundamental group of the regular part of X is finite. This can be considered as a version of Campana-Abelianity conjecture, is implicit in the work of Greb, Genancia, Quebecus, but the only place where I found it explicitly written is in a paper of Wang Wang. And the other implication that I would like to discuss today is that the Nagai conjecture that actually concern degeneration of X imply the existence of the so-called Hodge octahedron. I will define it, but you need to think of it as a refinement of the Hodge diamond, a 3D version of the Hodge diamond. Okay, let me proceed in order. Let me recall first the definition of irreducible holomorphic symplectic variety, and I'll make some comment on the definition itself. Yes.
Some structural integration and then include about everything, or you are restricting yourself to.
So what we will prove is that if there exists a Lagrangian fibration, then the fundamental group is finite. Yeah, the expectation is that as long as the B2 is greater than 5, this Lagrangian fibration should exist. That's what the SYZ says. So let me start talking about the finiteness conjecture. So in general, let's say that Y is a complex scalar or projective KLT variety with K of Y numerically trivial. Then the Boville-Bogomolov decomposition, proved by several authors, I mean, Druel, Greb, Genancia, Quebecus, Öring, Petterner, at least in the singular case. Otherwise, we need to go back to Boville. Says that there exists a quasi-étal cover of Y. And quasi-étal, remember, that means that is étal in codimension 1 or étal on the smooth locus, codimension 1, up to a quasi-étal cover Y split in a complex torus may split in this way. A strict Calabi-Yau, a product of strict Calabi-Yau, a product of irreducible holomorphic symplectic variety that I will denote by X. And the standard definition now of irreducible holomorphic symplectic variety is the following. So if let's fix X a normal, so let's say that X is a normal variety with a canonical singularity. Actually, I could require only rational singularity, but then what I will say afterwards will imply canonical. And so this is the standard definition, but for this talk, let me say that this is the weak definition. Says that X is IHS if for any quasi-étal cover X tilde X, then the algebra of reflexive differential of X is generated by a symplectic form. You see, it's a bit strange to define a property of a variety prescribing a behavior of all its quasi-étal cover. It's kind of natural from the perspective of the Boville-Bogomolov decomposition. But I mean, it's a priori a lot of data that you need to fix. But I need to see. No, exactly. And actually, this has been already proved by is a result of was probably a working assumption when it was developed. But then later, Greb, so Genancia, no, Greb, yes, Genancia and Quebecus, using result of Campana, prove that the algebraic fundamental group of the regular locus is actually finite. So maybe let me point out here when I say that there exists a quasi-étal cover, doesn't mean that there exists a unique one. For instance, if you have a complex torus, you can always take an isogeny. But you can wonder if on this other side, there is maybe a maximal cover that one could take. And what this says is actually we could take the universal quasi-étal cover. And so give maybe another definition of irreducible holomorphic symplectic variety, maybe the strong definition is the following. Maybe X is IHS if, well, I require the generation of the algebra of reflexive differential by a symplectic form, and I impose, and if I want, I could actually, I could take the regular part, no? It's the same algebra, and requiring that the algebraic fundamental group is trivial. Aesthetically, this is a nice definition because it's really symmetric to the one that we gave in the smooth case. No, the same definition. We don't involve quasi-étal cover. This is a bit more general in the sense that it involves also some quotient, finite quotient of this variety. But for the point of view of the Boville-Bogomolov decomposition, if we want to identify the minimal building block in this decomposition, this is better. especially for model A problem, is kind of pointless to parameterize also many finite quotient of these objects. But then there is a natural question that arises. Do we really need to take the profinite completion? Can we take the topological fundamental group? And that's like actually a tricky question. No, the problem is residually non-finite group that may arise. We don't know. So the question, the finiteness conjecture, is that actually the topological fundamental group of this variety is actually finite. And if it's finite, then we could remove the profinite completion here. Yes, if it's smooth or as quotient singularity, then this is already in the paper of Beauville. There is an argument, an analytic argument, Cheger-Gromol, that granted that the fundamental group, that these are simply connected. Okay. The problem is that this analytic technique uses the completeness of a metric. And when you start removing the singular point, that's not good. With quotient singularity, you pretend that everything is smooth, maybe the stack is smooth. So you are not removing anything, so you don't destroy the completeness. So Lucas Brown actually is working in that direction, try to understand a metric approach to prove the finiteness. Today, I would like to give you a strong geometric evidence of the conjecture, namely that if we impose that the irreducible holomorphic symplectic variety admits a Lagrangian fibration, then the theorem is true. So theorem by Filippazzi, myself, and Mauri, that the conjecture holds if there exists a Lagrangian fibration f from X to Z. And if we consider that the SYZ conjecture says that if the B2 of X is greater than 5, then a locally trivial deformation of X should admit a Lagrangian fibration we obtain the following corollary, that if V2 of X is greater than 5 plus we believe in SYZ, then we obtain the finiteness conjecture. The deformation is locally trivial. The fundamental group of the regular part doesn't change. And I would like to sketch the proof of this result. The proof.
Sorry.
Yes.
Why the SYZ conjecture is supposed to be true after even locally trivial deformation? Is it possible that after such deformation, B2 becomes 1, for instance, so that there's no Lagrangian fibration?
No. The locally trivial deformation preserve the B2.
Yes.
So.
Yeah. But,
yeah.
Is one which is locally trivial outside the central point, right?
No.
Otherwise,
locally trivial. If there exists a locally trivial deformation.
Or maybe the Picard rank. If the Picard rank is 1, then there is no fibration.
No. I'm not saying that any locally trivial deformation.
So some
there exists. Then there exists a locally trivial deformation that admits, for sure.
Sorry.
There should be some divisor where Mhm. Yes. And you take a locally trivial deformation of it. So the equisingular, yes, yes, yes. No, locally trivial, locally analytically. Yes, they will be homeomorphic, but the complex structure is changing. Yeah. Yeah, I mean, if it was smooth, then it would be a smooth deformation. Locally is a trivial deformation. And I'm just requiring that the singularity aren't changing. If the singularity are changing, then you will modify the fundamental group of the smooth locus in general.
So smooth case tells you that you just erase this part of the deformation, so it just tells you.
I mean, a smooth deformation for sure is locally trivial.
So it states that from the beginning from X, always.
Oh, no. So you deform and yeah. You need to deform, yeah, because you may have Lagrangian variety which do not admit any F class with an isotropic element. So if you have Picard 1 generated by an ample class, there's no way that you can get a Lagrangian fibration, but you should deform it to a divisor. Yes. Yeah.
And a corollary is
Not a well, spatial Lagrangian may be fine as well, because then you hypercolor rotate it, you make it holomorphic. But
so could I ask also corollary is finiteness conjecture holds for what? For any locally trivial deformation of X or
yeah, I mean this conjecture is invariant by locally trivial deformation. Yes, to exactly. I mean, another way to rephrase the SYZ conjecture in closer maybe to the abundance conjecture would be that if you have an F class, then it's actually semi-ample. And so what you would like to do is first to find with this lattice theoretic way a class that is isotropic. You deform the hyperkähler in such a way that it becomes actually an F class, and then if it's semi-ample, you get the Lagrangian fibration. Okay, so let me sketch the proof. So first, we can reduce to X projective. It's local Torelli and an argument of Matsushita. This is very small deformation. So the first things is that I won't really prove the finiteness. I will prove that the fundamental group of the regular locus is virtually abelian. Because this implies finite. What does it mean virtually abelian? It means that our fundamental group is an extension of a finite group and an abelian one. But for the time being, I'm not saying that the abelian part is finite. But I'm saying that the two are actually equivalent. Why? Well, you could use this result that the profinite completion needs to be finite, because if you take something that is virtually abelian infinite, then its profinite completion should be infinite as well. But it's a contradiction. But okay, for virtually abelian, since I didn't prove the result, let me say up to a quasi-étal cover, we can clear this finite part. So we can pretend that the fundamental group is actually abelian. But then what is the tensor of A tensor Q? This is the H1 of the regular locus over Q. And this is the same as the H1 of XQ. So you can use the fact that KLT singularity as finite, locally finite fundamental group. Actually, I have a proof also for projective rational varieties, but this should be classical. It would be interesting to find a reference, and probably maybe without the assumption of the projectivity. I think that this works in the rational case with no other assumption. But we work with Hyperk variety, so this is actually 0. So we obtain that the rank of A is 0, no? Okay, great. So now we want to realize geometrically this excess sequence, and we use the Lagrangian fibration for that. So this is step 2. This is the Lagrangian fibration. And now I want to restrict on a saturated open set of X over which, so I take an open set in Z over which the map is actually smooth, okay? So by the homotopy X sequence, I have that it seems that I'm in business. Let's say that F is the general fiber, but the general fiber of a Lagrangian fibration is a torus. So this is actually, if there's a dimension 2n, this is Z, well, 2n, well, whatever. So it seems very similar to the X sequence that I wrote, but this is just the smooth locus, not the regular locus. What is the difference between the two? The picture is something like that. So suppose that this is one singular fiber, and why? Let's say that here we have, let's use a color. That here I have a singular point, okay? And actually this is also a singular fiber, okay? So the fundamental group that I'm computing is the complement of this fiber here. But what is the difference with respect to the regular locus? Well, this is an open set in here, so there is a surjective map here. But we have also this loop that winds around I1, I2, that winds around these divisors. And that's actually the only difference between the two. The kernel actually is generated by this gamma I. Now, how the fibration looks like locally there is something like Zi that is sent to Zi to the Mi. No? Locally, in the normal direction, is just a map of curves. So locally, the maps look like that. Let me define M, the GCD of all the Mi, actually MJ, of all the Mi, such that gamma, if this is F of gamma I is Cj of Mi, where Cj is a loop around here. I'm just saying a triviality that if the local model of the fibration is like that in the neighborhood of this point, this loop gamma I is sent to M times these loops. Yes. I'm fixed actually a divisor on the base. Yes. If you want, this is the normal slice of the divisor. But okay, what is this GCD? It's just the multiplicity of the fiber. the multiplicity of the fiber. So in particular, if I take the image of f gamma I, this should be generated by Cj of mi. And here I have a copy of Cj for each of the mi. The I runs in an index set that is bigger than the j. But I can clear them taking the GCD. And so this is actually Cj of mj, the multiplicity.
So could you clarify a bit? So what is the multiplicity of the fiber? If there is multiple components with each with different multiplicity, what is the?
Is the GCD of each. So if you have a divisor below and you take the preimage of the divisor, each irreducible component will have some multiplicity. Yes. Take the GCD of this multiplicity. This is by definition the multiplicity of the fiber, of the whole fiber.
Okay.
Yeah, okay. Maybe Campana. Yeah. At least here, that's the right one to take, I would say. Why? Because, I mean, I can take the kernel. So this is surjective by construction. If I take the kernel of this, what I obtain is the fundamental group. I mean, this, now, for me, this will be just a definition. Is the orbifold fundamental group of the pair given by 1 minus 1 mi. And here I have the divisor delta I, where delta I is this divisor here. And I call all of these delta for brevity. Actually, this can be found in a paper of Campana. It works for more general vibration that he called the net vibration. Okay, it's quite classical for curves, but okay. Okay, so you see, we have constructed an extra sequence like this. What we miss is proving that this actually is finite. And for this, we need some birational geometry. Step 3, we use the canonical bundle formula. That says that the canonical of the total space is the pullback of the canonical of the base plus a divisor plus a linear series M. And the only things that we need to know is that B is greater than our boundary delta, is the same B that Birkar defined yesterday, and he has something similar also. M is pseudo-effective. I can say in this way, in this case, because Z has Picard number 1. And okay, the pair ZB is actually KLT. Okay, so in particular, what we obtain from this is that the pair we care about has the property that KZ plus delta, well, since this is a perkeler, this is linearly trivial. But our pair is obtaining shaving this generalized pair, throwing away the moduli part, and eventually a bit of B. So in particular, this is greater or equal than 0. Okay. Minus, yes. So there are two options. Either the pair Z delta is Fano, is log Fano, or is Calabi-Yau. And I want to rule out the case, the Calabi-Yau case. Remember that rho of Z is equal to 1. Because we are in the hyperkähler world, and the base of the Lagrangian fibration has always Picard 1. Yes, yes, yes. Well, I'm using just Picard 1, so. Yeah. No, 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 no. Yes, yes, yes. Yeah, yeah. Also yesterday, Birkard, when he was using this. Oh, you mean for rho of Z is equal? Yes, yes, yes. It's also in general. Yeah, yeah. I use here the equidimensionality for a net vibration in the sense of campana. I mean, you can see also why. If I start blowing up some divisor there, there will be new loops like that that I'm not really controlling, pulling it down. So it's really important, the equidimensionality. Yeah, but indeed is a good. Okay, now you will see when I rule out the Calabi-Yau case, that's actually important, that I'm working with an hyperkähler with an irreducible holomorphic symplectic variety. Why? That's a funny argument. So if I start with X, Z, and here I have my pair delta, look at delta. The coefficients here are standard coefficient. This means that I can take a cover, which is called the index 1 cover, which has the property that Kz is equal to the pullback of Kz plus delta. Okay, because this was Calabi-Yau and this is a standard coefficient. So this is an irreducible holomorphic symplectic variety. This is Fano, and by construction, this is Calabi-Yau. Okay, now I take the base change, the normalized base change. Hey, because Kx plus delta is trivial. It's linearly trivial. Usually the index 1 cover is only locally because you cannot grant this globally. That's the only problem. Exactly.
But what happens if delta is 0?
Delta is never 0 because that is Fano. Okay. Now I'm taking the normalized blow up, but this is a very special cover. What I'm doing, if here I have one divisor with coefficient m, then this cover has precisely ramification m, maybe followed by an étale cover. Now, if I have a fiber of multiplicity m, and I take a base change precisely of ramification m, and I take the normalized blow up, at the general point, this map is étale. So this map is quasi-étale. But by definition, this should be, again, an irreducible holomorphic symplectic variety. Contradiction, because I cannot fiber over a Calabi-Yau, because the image of an irreducible holomorphic symplectic is always Fano. So this cannot happen. The Calabi-Yau case cannot happen. So we are really in the log Fano case. And the step 4, I write it here, is to use the result of Lucas-Brown that says that the orbifold fundamental group of log Fano pair is finite. And this concludes the proof. Actually, The expectation is that there are finitely many deformation class of irreducible holomorphic symplectic variety. So now we prove that the fundamental group of the regular locus is finite, but actually we expect that it is bounded in each dimension. We can already prove that it satisfies the Jordan property, essentially because these orbifold, we can prove boundedness for this pair, so we know that only finitely many group appears here. And so from here, you read the Jordan property. But for the boundedness in general is still open. And the problem is actually, if I take an automorphism of an irreducible holomorphic symplectic variety that acts trivially on the H2, I want to know that the order of this automorphism is bounded with the dimension, which is the question that I asked to somebody in the audience in these days. Okay, but this was the first part of the talk concerning the fundamental group. I would like now to move to cohomology, actually, and talk about Hodge octahedron. And I would like to first give some idea of what this object is. Now I need to work in the smooth case, or quotient singularity, or isolated singularity, or symplectic resolution, but I cannot work in the for an arbitrary irreducible holomorphic symplectic variety for a point that I will highlight later. But let's say it's smooth. And let me show you what it means, at least for a K3 surface, what this octahedron is, K3 surface. So we know that the Betti number of a K3 surface are 1, 0, 22, 0, 1. And the nice things of displaying in this way is that I can see that this string is palindromic. I see Poincare duality. I can upgrade this picture to the Hodge diamond. One, 0, 0, 1. 21, 0, 0, 1. If I sum along the row, I get back the Betti number. But the advantage of this, is that I can display another symmetry that is complex conjugation. And for hyperkähler manifold, what I'm claiming is that you can upgrade this picture to a three-dimensional picture. The Hodge octahedron. And the number that you see in the octahedron are 1, 1, 1, 1, 18, and 1. And again, you see, if I sum along rows, I get back the Hodge diamond. And actually, there is a new symmetry that we can see, that is the rotation by 90 degrees. That is the so-called P equal F, perverse equal Hodge, first discovered by Shen and Dean. This is something that was completely invisible at the level of the Hodge diamond. Let me give you maybe some cycle. So this number actually represents some cohomology classes, no? So if I call sigma the symplectic form, and suppose that the K3 is elliptic. So I can take beta, the pullback of the O1, and I can take eta, a representative for the image of H2 of X to of the restriction of the H2 to one elliptic fiber, the general one. So if this one represents sigma and this one represents sigma bar, then this is sigma bar, this is beta, and this is eta. So you see, I'm saying you won't never see this symmetry from the Hodge diamond, because what this does is exchanging this 1-1 class with the 0-2 class, okay? And another remark is that this comes from the Hodge decomposition, but this comes from some filtration. So here actually you have many choice for gamma. What actually I'm representing is some graded piece, not actually a canonical decomposition. No. The only things that you need is an isotropic class in the H11. Yes. Yeah. Maybe I want to describe a bit more about, yes. There is, I cannot draw it in the board. Maybe one funny, this was classically known, but what? Oh, yeah. I mean, for the H2, the picture is always like this in any dimension. I mean, 4 vertices with 1, 1, 1, and then the middle one. No, that's just the Verbisky component. Then there are some other components in the cohomology that doesn't come from the H2. Yeah. Exactly. I wanted to describe it. Yeah. So where this refinement actually comes from? We need a piece of linear algebra. So let's take V a vector space and then a nilpotent operator. Of index L. Which means that NL is different from 0 and NL plus 1 is identically 0. Okay. Now we know that there is a weight filtration that is associated to N, an increasing one from W0, W1, and so on, W2L minus 1, W2L, and this is V. With the property, two properties that define this this filtration, that's if I apply so this is increasing, but if I apply the nilpotent operator, I go back by 2. And then there exists, if I apply the k powers of n to the graded pieces of this filtration from L plus k to L minus k, then I get an isomorphism. Let me give some example of these, some geometric example of this filtration. So if X is an hyperkähler manifold, and sigma bar is the antisymplectic form, then I can take as nilpotent operator the cup product in cohomology with this antisymplectic form. It's a nilpotent operator because after a while it needs to vanish. And then I can consider the filtration associated to this nilpotent operator. And what I get here in the second point, maybe 2, what I get is an isomorphism, N minus Q, between these pieces of the Hodge decomposition. Maybe it would have been easier to see the complex conjugate of these is just it comes just from the fact that if you take omega q and then you take omega 2n minus q wedging with sigma 2n minus q. Okay, the symplectic form induced this isomorphism. And so what is the weight filtration for this operator on homology? Is just the Hodge decomposition. Yeah, exactly. That's the point. We don't know this in the singular case. Of course, we won't work with homology, but with intersection homology, otherwise it's not pure as a Hodge structure. But if we knew this for intersection homology in the singular case, then what I said would go through with no change. It would be an Hodge octahedron in intersection homology, though. Well, quotient would work, yes, yes. Quotient, yes, is fine. Let me introduce another filtration that comes from the Lagrangian fibration. So this is Lagrangian. I can take again the pullback of an ample class on Z, and then the weight filtration associated to this operator. This is actually defined over Q. If the morphism was smooth, this would be the Leray filtration. But in general, this will be the perverse filtration, the perverse Leray filtration. So this is the perverse. And what I represent in the Hodge octahedron definition, the entry of the Hodge or perverse Hodge octahedron that now are three-dimensional, so IKD are equal. So what I can do, I can take first the graded piece with respect to the perverse filtration. Essentially, because this is H11, these graded pieces are actually Hodge structure, pure Hodge structure. I can take the PQ part of this. And without messing the coefficient, is this one. So what I'm saying here, essentially, that I take my homology, degree D. I filtered first with the perverse filtration. I filter again each pieces with the Hodge decomposition. So that's why at each level, I have two degree of freedom. It's perverse and Hodge. And where the symmetry actually comes from, the fact that I recall this definition of the weight filtration for an nilpotent operator is because you see the definition of the Hodge filtration and the perverse filtration are actually very similar on an hyperkähler manifold. They are all coming from analogous nilpotent operator, the capping with an isotropic class. And so, I mean, the symmetry comes from the fact that if I take the special orthogonal group of the H2 of the Hyperk with respect to the Boville-Bogomolov form, actually one can prove that this is contained in the image of the map defined in the following way. I take the automorphism of the cohomology and I restrict it in degree 2. Okay, this comes from the LLV algebra. But what this is telling us, that if I take a ring homomorphism of the whole cohomology and I restrict to H2, then inside this group, I have this SO, which means that I can exchange beta and sigma bar. So these are two isotropic classes. So with a special orthogonal transformation, I can exchange one with the other. But because of this containment, I can lift this orthogonal transformation to an actual automorphism of the whole cohomology. But this means that with this automorphism, I'm sending one filtration to the other. I'm sending one filtration to the other. That's how we exchange the two. But Shen and Dean have another, not in the original paper, but in a new paper that they wrote, they have also another nice description of this symmetry. So let's take the following Lie algebra. The Lie algebra generated by decapping with X is a class in the span of sigma bar, beta and eta. Okay. And then H is just the usual counting operator. It's just on the whole cohomology in acts in each degree by this integer. That's not really important. So this is a part of the LLV algebra, actually. But using the result of Verbitsky, you can prove that this is SO6. Okay, the 6 comes from 4 plus 2. It's always like that. 2 is just a unit, hyperbolic lattice. But so SO6. What are then the HIKD? These are the rank of the eigenspace for a Cartan subalgebra of SO6. No, you take the Cartan subalgebra, you let it act on the whole cohomology, you get SO6. The Weil group of SO6 are the rotation of the octahedron. So this rotation here can be interpreted in terms of the Weil group of this SO6. Just the rotation, no? Here you have the conjugation, is a reflection, is not a conjugation. But what Shen and Dean say, okay, maybe let's add also an ample class, so that here you get SO7, and then the Weil group in this case is the full rotation group of the octahedron. So if you add another class in the cohomology, the Betti number is sufficiently big, then you can recover the whole symmetry. Also the conjugation by this argument. But for the time being, this is just the symmetry. I haven't said why this should be an octahedron. And that's what I would like to say in the last part of the time. Why an octahedron? Well, let's fix D. So I want to slice the octahedron at a certain level. And now I have a graph like this. This is my I, the Hodge structure, and K, the perversity. Now, what we know about IKD? For sure, this is 0 for I greater than D. I'm just saying that in degree D, my Hodge structure has level D. But because of the symmetry, also K should be greater than D. So we have something like that. This is not yet the octahedron. To get the octahedron, I need to say that the support, the convex hull of this HID is contained in this diamond. So that here I have some 0. This is some new additional vanishing that we need to prove. How can we prove them? We can try to give some interpretation to the diagonal of this picture. The sum of the HI along the diagonal are the rank of the graded piece of another nilpotent operator. Of the weight filtration, of which operator of L beta, so the conjugation by beta, and so with L implicitly here I'm thinking of Lefschetz operator, with gamma the dual Lefschetz operator of sigma bar, which should be the contraction by sigma. I mean, what I'm really thinking is that I mean, this is not a Lefschetz class, so it's not really, doesn't really make sense to talk about Lefschetz operator, but you can write beta as combination of Lefschetz class and sum together. But okay, the important things is that, I mean, you can guess that with some manipulation of this operator, also this diagonal here are can be interpreted in terms of this weight. But what is the nice things of the weight filtration? That the length of the filtration depends on the index of the nilpotent operator, in the sense that if I apply this nilpotent operator, I will scale by 2, but if I manage to bound the index of this, then I have a bound also for the diagonal where the HIK are actually supported. So the existence of the Hodge octahedron is equivalent to bound the index of this operator. And I'm saying that this has an important geometric meaning in terms of degeneration now of hyperkähler manifold and not no longer fibrations. And it's the so-called Nagai conjecture. The Nagai conjecture says the following: suppose that pi is a degeneration of hyperkähler manifold with unipotent monodromy. To this change, you can always grant it. Then I can take n2k. This is the logarithm of the monodromy on H2k. I said that the monodromy is unipotent, so it makes sense to take its logarithm. And the Nagai conjecture says that the nilpotency index on N2k is equal to k times the nilpotency index in degree 2. The usual philosophy that property of hyperkähler manifold should be controlled by the H2. And one instance here in terms of monodromy is that the nilpotency index in high degree should be controlled by the one in degree 2. And what we know, let me just say, the nilpotency index in degree 2 can be only 0, 1, and 2, as long as the level of the Hodge structure. And the only open case, open only for nilpotency index equal to 1. Is known for all known hyperkähler manifold for D equal to N, the maximal one, well, the middle one, is known in dimension smaller than 8, and I refer to my paper with Daniel for all the reference. But what is the relation with the Hodge octahedron? That's what we prove in there. Smooth case, yes. Oh, right, manifold. Yeah. Well, that's just the conjecture. So, so the following theorem, myself, is that the Nagai conjecture in nilpotency index 1 is equivalent to the existence of the Hodge octahedron. And the reason is the following, that if you compute the image of N2 when the nilpotency index is 1, you realize that this is actually an isotropic plane generated by two elements, W1 and W2. And the nilpotency index, using again the whole logarithmic monodromy, is just LW1 omega W2. Again, here you need to use the LLB algebra. So you see formally, or maybe I just erased, is formally identical to the operator that we saw before. And so what's the only things that you need to do now is to exchange the two isotropic plane with this other isotropic plane. So you bring one operator into the other. It's very beautiful that you see, I explained to you the additional symmetry, P equal F, the symmetry of the rotation by 90 degree of the octahedron, say that it boils down to send an isotropic class into another isotropic class. This result follows from saying that you take an isotropic plane and you send it to another isotropic plane. And then I think that we cannot do any further, go to three-dimensional space. Oh, that's a good point. Already here, there are some trouble in B2 equal 4. B2 equal 4 is like working in P3. Having an isotropic plane is like working with lines over a quadric in P3, P1 times P1. So you have two rulings. But then you can fix it. As I said, the important thing is that you have a class, an isotropic class in the H11. The action is transitive on each of the two rulings. So if I exchange beta with eta, I can fix this. Then for a higher quadric, the action is transitive. But then, yeah, when you rise in dimension, you have this problem of the transitivity. You lose, I think, any geometric information also. Yeah, what is left is actually settle completely the Nagai conjecture. And with this, I thank you for your attention.
Thank you very much. Any questions?
Easier, no, but maybe a way. So I think that we have explored all the algebraic trick that you can play here with the Nagai conjecture. Now, this is maybe a possible new direction where, as I said, this becomes a problem of vanishing now, prove new vanishing. I need to mention that Green, Kim, Lazar, Roble have actually an alternative description of how, I mean, an alternative strategy to tackle the Nagai conjecture. Essentially, it works saying, okay, you have actually a Lie algebra that acts on the cohomology of an Hyperk manifold. You can take its decomposition in irreducible, and you can study which irreducible satisfy the Nagai conjecture. And then you formulate a conjecture that the only irreducible that appears in the decomposition in irreducible of the cohomology of the Hyperk are of this type. So it's some condition of the dominant weight. But I think that we are at the stage that really some geometric input is necessary. Maybe, okay, another thing is Christian Schnell recently has a paper about Lagrangian fibration, and he can prove that these numbers sit inside a rhomboic dodecahedron, which means a polytope that is slightly larger than the octahedron, but we are going in that direction.
So are there any explicit example for which you can write down the octahedron explicitly? So higher dimension or?
Yeah, I haven't tried, but I think Hilbert 2 is fairly possible. Yeah. Yeah, maybe one remark about this. With the Hodge decomposition, we know that the odd Betti number should be even. With the Hodge octahedron, we know that the odd Betti number needs to be divisible by 4. That actually was known by Fujiki already. But this is a nice, you see it visually, why it should be divisible by 4. The odd one, yes. The orbit, exactly. SO6.
But the ways for representations of SO4, they look kind of different. Yeah, they kind of like different. It's very it's very difficult to keep one shape like that. It's very special.
I think that also Christian has something like that. It has an SL3 action. There are many actions here, but the SO6 gives right that one. But you really need to go SO6, otherwise you don't see some of the action. That's yes. So you get a more. You mean for a smaller Lie algebra?
That's a very strong property of weights for representation.
I don't see it on this post.
Are there more questions?
No. There are just there are counterexample. P113 may arise. Yeah, but I haven't seen any. So if you use a conjecture of Kolar that says that if you have a map from a smooth variety, a finite map from a smooth variety to another variety, this variety should have quotient singularity. Not saying that this is Galois, just saying that it's finite. This would imply that even in the singular case, at least, the base should have quotient singularity, not just KLT. But I haven't seen any conjecture of the actual shape in the singular cases. It's just some quotient of Pn or small tree. For the time being, all the example arise in that way. We know it's Fano. We know that it has the cohomology and the intersection cohomology of Pn. We don't have example of that, but yeah, there's no invariant that prevents it to be a weighted projective space. Yeah.
Any more questions?
Okay, also that is a kind of quotient of Pn.
So more questions? If not, then let's thank Mirko again.
Thank you.